Okay, so 4.4 is all about theorems of the zeros of the polynomial. So remember, zeros is the same thing as solutions, as results, as x-intercepts. They all mean the exact same thing. So everything that we cover today is a theorem about a possible zero or solution to these polynomial functions. There's a couple of really good theorems that help us to find all of our zeros. And so that's what we're going to do. We're going to learn some theorems, then we're going to find some zeros and see how these all play out. So the first theorem, and it's on the handouts typed up for you, is the fundamental theorem of algebra. This is kind of a big one, thus the fundamental theorem of algebra. It says every polynomial function of degree n, where n is greater than or equal to 1, okay, so you have to have a variable of some kind in this polynomial function, that has at least one zero, or it has at least one zero in the set of complex numbers. So every polynomial that has a variable is going to have at least one zero. And like I told you before, if it's a third degree polynomial, you could have up to 3 zeros. Okay? You could have 2, you could have 1, but you could have up to 3. It goes on to say that every polynomial function of degree n, where n is greater than or equal to 1, can be factored into a linear factorization, where you have n numbers of linear factors. That's where you have a constant, that's what this a sub n is, and then you have x minus c sub 1, x minus c sub 2, x minus c sub however many you have, all the way to c of sub n. All of those c sub numbers are your zeros. So when we factor our quadratics out and we get, x minus 2 times x plus 1, we set each of our factors equal to 0, and those are our solutions. Those are our answers. Those are our zeros. That's what this is saying, is that every polynomial function can be factored. As we are going to see, though, our factors can be in the complex numbers, which means they could be real, they could be imaginary, they could be a combination of both and thus be complex. We can also have radicals at play here. So we can have irrational zeros, which are something we haven't really dealt a lot with, but you can have those as well, and they come up. So the first style of problem that you could encounter is where we have to find a polynomial function, and then they give us a degree, and they give us the zeros. And we need to write this function out. And so the way that we're going to do it is we plug in the zeros they give us into that factored out form, where we have a sub n equals x minus 1, because they told me a 0 was 1. X minus 3i, because they told me one of my zeros was 3i. And x plus 3i, because they told me my other 0 is is the minus 3i. Minus minus gives me plus. Now, that still doesn't give me what my polynomial function is, because I don't know what that a sub n is. And so we got to figure out what a sub n is. We're going to let a sub n be 1. If we let a sub n be 1, then we can do all of our factoring, or excuse me, not factoring, our foiling to get down to our polynomial function. So if they don't specify an a sub n, we're going to let it be 1, because that makes our life a lot easier. Because it doesn't say find the polynomial function. It doesn't say that there's only one. It says find a polynomial function. And that's what we're doing. We are finding the polynomial function when a sub n is 1. Because algebraically, that is so much nicer than if we let a sub n be 5 or negative 3 or negative 2/3 or whatever. Because I don't want to factor and FOIL and do all that kind of stuff with all those things. I can tell you I don't personally love this style of problem, so you won't have a lot of them. The reason why I don't love it is because you're really not doing a ton of algebra except for a lot of foiling. And I would hope when you're halfway through college algebra at this point, we can do some foiling. So I'm not going to give you a ton of these. They are good to see how it kind of all plays out. But in terms of growing your mathematical capabilities, I'm not sure that these are big muscle builders. But we're going to do one more, because we're going to do one that has multiplicities. Because that first one didn't have any multiplicities besides 1. And if you remember, multiplicity tells you how many times you get the same 0. So this time, we have a 5th degree polynomial. We have zeros of -1. We get that 3 times. 4, we get that once. And 0, we get that once. Notice if you add up the multiplicities, you do get the degree of the polynomial. Which is also true for the one above. It's just all the multiplicities were 1. So when we plug those in to our general expanded form, we have f of x equals a sub n. We have the x plus 1, because that's our -1, 0, raised to the 3rd power because of the multiplicity of 3. Then we have x minus 4, which just has a multiplicity of 1. And then we have 0 with a multiplicity of 1. Remember, the way we get 0 is just by having an x. If that would have said 0 with a multiplicity of 2, then we would have just a simple x squared there. Now we're going to do the same process. It's just a little bit longer. We're going to let that a sub n be 1. And then we've got to factor or foil it all out. Which again is why I don't love this problem.
So why do we still get an x if the factor is 0? Is it like a placeholder?
It's not a placeholder. What it is that, like, let me show you a basic one. If we have x squared minus 8x equals 0, how do I factor this? I pulled the x out. And so now I would set x equals 0 and x minus 8 equals 0. And so that's where, when it tells me one of my zeros is 0, I know that that leads me back up to an x. Does that make sense? Mm-hmm. Okay. That's a good question, but that's how it works. So you have to factor, foil. I keep saying factor when I mean foil. You have to foil all this stuff out, which for x plus 1 to the 3rd, you have to know how to expand the sum of a cubic, which is here, which again is why I don't love these problems. If there's any of these on your homework, there'll be 1. There will not be any of these on a test, because again, going this direction isn't super helpful. What is helpful is when we start with the big long polynomial and we have to get our zeros. That's really the meat and potatoes of this chapter, is getting the zeros. And so that's where these other theorems are going to come into play. They're going to help us find those zeros. Because sometimes, as we've seen on previous homework, the stuff doesn't factor as nice or as noticeably as we would like them to. We don't really have a lot of good tools for factoring x to the 5th, like this really long polynomial. But we did learn in 4.3 how to do some synthetic and long division, which will help us find these zeros. And that's what we're going to use in order to help us find zeros and thus simplify our polynomials down to quadratics. Because quadratics, we have so many different ways to solve quadratics. We've got the quadratic formula, completing the square, factoring. What else do we have? The square root principle. So if we can get our polynomials down to a quadratic, we've got all these different tools to solve and find the remaining zeros from those. And so that... Yeah, that's what we're going to use. We're going to use our divisions to get down to the quadratics, and then we're going to be able to finish solving and getting all of our zeros for these. So it is nice whenever they give you your polynomial already in the long factored form, like if they give it to you like this up here, because then you don't have to do any factoring, and you just set each of those equal to 0, and you know what your zeros are, and you're able to graph and do all that kind of stuff like we did earlier in this chapter. Are we ready? Move on to something that's a little bit more mathy. Okay, so you guys have this on the handout, so don't feel like you have to copy this down. These are the zeros of polynomial functions with real coefficients. And so there's two different types of splits that we're going to talk about for a second, where if we get zeros that are not real, aka we get complex zeros, what happens there? Or if we get irrational zeros, aka we get zeros that have radicals involved. Those are kind of ones we haven't really played with. We've played around with, we get 0 as 0, and we get 3 as a 0, and we get all these nice numbers. But what if the numbers aren't quite so nice? The nice thing is that if you get a complex answer, like an A plus BI or an A minus BI, where B does not equal 0, so you get a complex answer, you find one of those, then its conjugate is also automatically a 0. So that's super nice. You don't even have to go find it. So if a complex number, A plus BI, is a 0 of a polynomial function with real coefficients, then its conjugate, which is A minus BI, is also a 0, automatically. So that's super nice. So short example is if 2 plus 7i, if we find that out to be a 0 of our polynomial function, we automatically know that 2 minus 7i is also a 0 of that polynomial function. And the same logic holds with our irrational zeros as well. If we have a plus c square root of b as a 0, where a, b, and c are all rational numbers and b is not a perfect square, if that is a 0 for our polynomial function f of x, then its conjugate, which is a minus c square root of b, is also a 0. So it's the exact same concept. So if negative 3 plus 5 square root of 2 is a 0, then negative 3 minus 5 square root of 2 is a 0. So those are pretty cool. They help us find our zeros a little bit quicker. So we're going to do, this is kind of like the first ones that we did. Except now we're dealing with either complex or irrational zeros. It says find a polynomial function of lowest degree with rational coefficients that has negative square roots of 3 and 1 plus I as two of its zeros. So this one kind of does both all at once. We know that we have a 0 of negative square roots of 3. They tell us that. Based on the information we just saw, what else do we know would be a 0? Positive square roots of 3. And it tells us we have another 0 of 1 plus I. So what's another 0? 1 minus I. And if we are trying to find the polynomial function of lowest degree, and we now know we have these as our zeros, what is the lowest degree this polynomial function can be? Fourth. That's right. So we could have a polynomial function of fourth degree. So we'd have f of x equals x plus square roots of 3, x minus square roots of 3, x plus 1 plus I, x minus 1 minus I. And then from there, we do all the fun boiling. I think think these beginning, like the fundamental theorem of algebra and these zeros of the polynomial functions, these little sub-theorem things, they're very helpful. But like I said, I think this long foil fest thing that your book does is not super helpful. So again, if you have one, you'll have one. You won't have any on a test. Because honestly, what ends up happening is, yeah, the concept of knowing what the zeros are is fabulous, but then odds are somewhere along the way, you're going to drop a negative. You're going to foil something wrong. I know I did, and I had to fix it. And so then it becomes less about understanding the broader concepts and more about just being really tedious in the algebra. And that's what drives people away from math, is the tediousness of it. And so I don't like to focus on the tediousness. I like to focus on the broader concepts. And so, yeah, this is great and all. You won't be tested on it like this. The big thing that I like you to notice is that if they give you a rational zero or they give you a complex zero, that you can automatically identify other zeros just based on these little theorems. Do we have questions on any of it that we've done so far? I think all of this stuff, while there's bits and nuggets that are really good from these first front and back of my notes, the next theorem is the one that you will use constantly. And it's the one that comes to play, and it's the one that's actually really helpful. And so if you look at your handout, that next theorem is the rational zeros theorem, aka the rational roots theorem. And I didn't put another parenthesis if that bothers me. I included both names because you'll probably hear me jump back and forth between rational zero and rational root. I learned it as the rational root. Remember, zero is the same thing as root, same thing as solution, same thing as x-intercept. So you could use any of that terminology. But I will probably go to the rational root theorem because that's how I learned it. And also rational root, there's two R's, so they kind of go together. So the rational root or rational zero theorem says you have this polynomial, this p sub x, and that means polynomial in terms of x, and you have a sub n, x to the n, a sub n minus 1 to the x to the n sub minus 1, all the way down until you get to your constant term. So don't let the weird mathy look of that polynomial function scare you away. What it shows you is that these a sub n's are your coefficient, and then you have your x terms. The n is the degree of the polynomial, and then you go all the way down until you get to your constant term. That's what this is, very general form of a polynomial function. So we have let p sub x be a polynomial function with integer coefficients. If p over q is relatively prime, what that means is if it's simplified, if p over q is simplified, they have nothing in common, and p over q is a zero or a root of your polynomial function, then p is a factor of your a sub 0, and q is a factor of your a sub n. So that's a lot of math to say one simple thing, which is what the fraction says. P over q equals the factors of your constant over the factors of your leading coefficient. That will help you solve so many of your polynomial functions. The two problems at the end of Monday's assignment for 4.3, when they don't factor really nice, this is how we're going to do it. We're going to use this rational zeros theorem to find a zero that we can test. Because, like Kelsey told me, she was like, I didn't know what to do, so I just started kind of guessing some random numbers to try and do synthetic division with. And that's originally how you would have to do it. Remember with synthetic division, we have our box and we put numbers in there, and if you don't know a zero for your polynomial function, you just have to guess and hope that you land on one. But think of how tedious that can be, because you're guessing out of infinite numbers to try and put a number in that little box. this is going to help you eliminate that to where you go down to like 9 numbers or 10 numbers or 13 numbers. Like, you're never going to have infinite numbers. We're going to cut that down into a manageable size. And so this is one that's actually really, really helpful. So let's do an example so we can actually see what in the world all this means. It says find all the rational zeros, then find all the actual zeros for this polynomial function. Because we might not have just rational zeros. We might have irrational or complex. So they give us a polynomial function. And if I look at this polynomial function, we have 3dx to the fourth minus 11x to the third plus 10x minus 4. It's a 4th degree polynomial. It doesn't have an x squared section. It's not a nice one to factor or anything, right? Like, that's going to be one of those ones that I don't know how to figure out a zero for it. So we're going to use our rational zeros theorem. We're going to list the factors of our constant over the factors of our leading coefficient. And I'm going to shorten leading coefficient to LC, leading coefficient. So what is our constant term for this polynomial function?
-4.
Okay, -4. So what are the factors of 4? 2, 1, and 4. So here's how it works with factors of our constant leading coefficient. We're always going to put plus or minus. Because if I have +1 and -4, I can get -4. If I have -1 and +4, I can get -4. So we're always going to include the positive and the negative. So you said plus or minus 1, plus or minus 2, and plus or minus 4. There's some combination of 2 of those that it will always give me -4. Okay? And then what about my leading coefficient? What's my leading coefficient? 3. So what are the factors of 3? 1 and 3. But again, I'm going to do plus or minus 1 and plus or minus 3. Now this is like a really weird looking fraction. I totally get that. So what we're going to do is we're going to consider all of our numerator numbers, so all the top numbers, in respects to our denominator numbers. So I'm going to look at 1 over 1. What does that simplify to? 1. What about 2 over 1? That simplifies to 2. What about 4 over 1? That simplifies to 4. Now I'm done with my 1 on the bottom. I have considered every number on top with respect to the number on bottom, and I've written those out. Now I do the same thing with 3. 1 over 3 would give me plus or minus 1/3. 2 over 3 would give me plus or minus 2/3. And 4 over 3 would give me plus or minus 4/3. So all of my possible zeros, every possible rational zero for this polynomial is right there listed now. Instead of having negative infinity to positive infinity be our listing of possible zeros, I have now gotten it down to 12. There's 12 possible zeros. 12 is a lot better number than infinity, if I'm going to be guessing. Because here's what's going to happen. In order for me to figure out if any of these are actual zeros, I'm going to use synthetic division. Okay? Sorry, I know it got all wonky. There we go. I'm going to use synthetic division to actually find a zero. So remember with synthetic division, I have my box. These are the numbers I'm going to test and put in my box. These possible zeros. Outside my box, I put my coefficients for my polynomial function. Now, I'm going to rewrite the polynomial function for a second because you need to make sure that we include our zeros, like our placeholders. It needs to be in descending order. I start with x to the fourth, so that's a 3, and then x to the third, which is a -11. I don't have an x squared term. That's where I put a 0 placeholder. My x term is 10, and then my constant is -4. We draw an arrow down from our first term, and we put it below the line automatically. So now, if we were doing it before today, we would just guess a random number to stick in that box. Now we don't have to do quite so much guessing. We're going to pick one of these, and we're going to put it in the box and see if it's a 0. So what number would you like to try first? Okay, I heard 1 first, sorry. So I heard positive 1, so we're going to try it. 1 times 3 is 3. Add down. 1 times negative 8 is negative 8. Add down. Add down. Add down. I did not get 0. Since I didn't get 0, 1 is not a 0 for this polynomial function. So right there I could eliminate one of the options. When it comes to this problem, I've had students, because now it's like, well, crap, I have to rewrite all that. And you do. Or I've had students who will get it all prepped, like all my blue stuff is all prepped in pen, and then they do all the red stuff in pencil so that when they get over here, if it's not a 0, they can erase it all without having to erase this setup. That's an option. I'm going to switch colors, and I'm not going to erase. And since I already have a 1 over here, I'm going to try a negative 1. Negative 1 times 3 would be negative 3, which would give me negative 14. Positive 14, negative 14, positive 4. Yay! We got a 0. So I know for a fact that negative 1 is a 0 to this polynomial function. So that means over here I have x equals negative 1. So if I wanted to write that as a factor, remember, I would move it over to the other side, so it's x plus 1 equals 0. There's my factor. And then remember, we started with x to the 4th, divided by x, so we're ending with x to the 3rd. 3x to the 3rd minus 14x squared plus 14x minus 4. And you're like, okay, that's great. And it is, but let me ask you this. If you're looking at this polynomial function in here, does that look like a nice factorable function? Like if I factor by grouping, I'm not going to get the same thing inside as outside. It's still kind of a mess, isn't it? So we're going to do it again. We're going to do it with this one. So we're going to do synthetic division, but we're going to do it with this polynomial here that we just got, where we have 3, negative 14, 14, and negative 4. And we're still going to use the original list of possible zeros, because really we're still dealing with the same polynomial function. We've just simplified it one step further. So we're still going to go back up here. We know positive 1 didn't work, but negative 1 did. We have that over here. So we're done with our 1s. Do you want me to give you a helpful hint on the next one, so we don't have to do it a whole bunch of times? Okay, let's do positive 2/3. You know, let's just jump down there to positive 2/3 so we don't go. I mean, you can go all the way down the list. I mean, that's the one bad thing about this rational roots theorem, is that yeah, it got us down to 12. And you could very well have to test all 12 of them. And that's kind of a bummer. But testing 12 is better than testing infinity. You know what I mean? So I'll take 12 any day. But let's take 2/3 times 3. That will give us 2. 2/3 times negative 12. Negative 8. 2/3 times 6. 4. Oh, look at that. It happened to be a 0. That's magical. So we found that 2/3 is a 0. So that was x equals 2/3. So if we want to write that as a factor, we will now have x minus 2/3 as a factor. Don't forget this plus 1 we had up here. And then we went from an x to the 3rd divided by an x. So we get down to 3x squared minus 12x plus 6 equals 0. Ignore this stuff down here. because I flipped the paper over. So we found 2 rational zeros, but now we still have this quadratic. We can factor out a 3, can't we? Now, I'm going to place that 3 all the way at the front, okay? That's going to be our a sub n. And that'll give us x squared minus 4x plus 2. Well, can we factor it? No, because then when I do my last, I'll have 2 times 2, which is 4. Because I need factors of 2 that add up to give me 4. The only factors of 2 are 1 and 2. Those aren't going to ever add up to give me 4. So when we can't just factor it, what do we do? Quadratic formula. Thank you. We have to use our quadratic formula. This is where we're going to get some non-rational answers. We found our 2 rationals. I mean, we could have only had 1. We could have had all rationals. But in this case, since this doesn't factor nice, we're going to get some irrational answers. So we're going to use our quadratic formula. Our a in this case is 1, our b is -4, and our c is positive 2. Quadratic formula is negative b plus or minus square root of b squared minus 4 times a times c all over 2 times a. 4 plus or minus square root 16 minus 8 is 8 all over 2. 4 plus or minus square root of 4 times 2 over 2. Which simplifies to 2 plus or minus square root of 2. So we have 2 irrational zeros as well. Which means, since we have to get our factor into linear factors, we have to get our function into this linear factors, which we had started. I'm going to probably have to turn my paper because I ran out of room. We had 3 times x plus 1 times x minus 2/3. And then now we have these 2 new zeros, where we have x plus 2 plus square roots of 2 and x minus 2 minus square roots of 2. Those are both minuses. That's a minus in there. Yep. That's one really long factorization. But remember, all of our zeros are going to look like x minus c sub n, where that c sub n is our 0. So if our c sub n is positive, then it's going to be best to put it in parentheses if it has more than one term. If our c sub n is negative, then it actually simplifies to look more like this, where we have x plus our c sub n. But this rational roots or rational zero theorem is how we find our zeros. It helps us to eliminate out so much in terms at the beginning of getting weird, like just randomly guessing things to plug in for our synthetic division. You guys want to do another one? Okay, let's do another one because we got time. This one I'll try to make a little bit nicer in terms of it'll all stay on one paper. We're going to do the exact same process for f of x equals 2x to the 5th minus x to the 4th minus 4x to the 3rd. It's 2x squared minus 30x plus 15. That's one big old long polynomial. So the first thing we're going to do is we're going to identify all of our possible zeros. Some of your homework problems could ask you for that. They want you to list out all your possible zeros. That means you need to find them using your rational zero theorem or your rational root theorem. We're going to look at our constant over leading coefficient. Factors of our constant. What is our constant in this long polynomial? 15. So factors of 15. Plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. All over our leading coefficient. Plus or minus 1, plus or minus 2. Great. So all of our possible zeros, notice we have 1, so that'll be plus or minus everything that's on top, because dividing by 1 doesn't change anything. And then we stick everything that's on top over 2. So we have plus or minus 1/2, 3/2, 5/2, and 15 halves. This long list of numbers is all of the possible rational zeros for this polynomial function. So now that we have our list of possibles, we're going to use synthetic division to find real zeros. And luckily all of our x's are accounted for, so we don't have any placeholders. We have 2, -1, and -4, 2, -30, and positive 15. Okay, and this is what we're going to do, because I don't want to do this 800 times. I don't think you guys want to do this 800 times. James, which one are you going to test?
Let's just do -1.
Okay, you're going to do -1. What one do you want?
+5.
Okay, let's see what you want.
I'll do positive.
Okay, Kevin, what you want? Okay, keep going. What do you want?
Let's go -3.
Okay, what do you want? Liz? Somebody's got to do one of these fraction ones. Oh, no, wait. That's a hint, hint. Somebody wants to do one of the fraction ones, I promise.
I'll do 3 quarters.
Okay.
I'll do 1/2.
Okay.
I guess it'll be 5.
Okay. Y'all test those. One of you has guessed the right one. This is why doing math like in groups is really nice, because then you guys can work together and not spend your whole life sitting here testing all of these. Whenever somebody finds a 0, let me know. Yep, 1/2. One half times 2 is 1. 1/2 times 0 is 0. 1/2 times -4 is -2. 1/2 times 0 is 0. 1/2 times -30 is -15. Doop, doop, doop. We got a 0.
That's an obvious problem.
It is a nice problem. So, that's okay. Fractions are our friend. Where they need to be. So our factor then is x minus 1/2. And then we started with x to the 5th, so we're ending up with x to the 4th. 2x to the 4th. Notice our x to the 3rds went away. So we have minus 4x squared. Our x's went away, so then we just have our minus 30. We can factor out a 2. We sure can. Because this is kind of gross, let's go ahead and factor it into the other one. Is that going to bother anybody? Where it's 2x minus 1, like that? I distributed it back into this first factor. If that bothers you, you can leave it out. Whoops, that's a 2. That's a really wonky 2. Sorry, guys. Okay, now we're down to x to the 4th. What do you think we should do? You think we should do it again and again until we get down to the quadratic? How do we factor x to the 4th? Yeah, notice we don't have an x to the 3rd term and we don't have an x term. So we have a trinomial that looks just like a quadratic. We have a x to the squared here. It's just squared twice. We have an x and then we have a constant. We can factor this just like it's a quadratic. Absolutely. So what we're going to do is we're going to factor like this. And instead of having just x and x, we have x to the 4th. So that means we need x squared and x squared. Now the sign in front of my c is negative. So that tells me I'm going to have a positive and a negative. And that also tells me I need factors of 15 that subtract to give me a negative 2. Positive 3 and negative 5. And we can test that. We can do our first, which will give me x to the 4th, minus 5x squared plus 3x squared. That would give me my negative 2x squared. And then that would give me my minus 15. So sometimes when they look big, bad, and scary, they do actually factor relatively nice. Now, before, when we've had, x squared plus 3 as one of our factors, what can we do? Like, how can we solve that? Can we set that equal to 0 and solve it? Yeah, we had a square root property or principle that we could use. So we have this factored into 3 factors. We can set all 3 of those equal to 0 to solve for the factors. Now, we don't need to do that here because we already know what that factor is. But we should do that for these other ones to get the remaining zeros. Because this isn't all factored into the nice linear form that they want. The nice linear form that they want is where you have x minus the 0. X minus the 0. And right now we don't have that because we have x squared plus 3 and x squared minus 5. So I'm going to set those equal to 0 to figure out what my remaining zeros are. So if I square root a negative 3, what am I going to get? We're close-ish. Plus or minus I square root of 3? Something like that? Yeah? Because what we have is the square root of negative 1 times 3. That square root of negative 1 becomes the plus or minus I out front. X squared minus 5 equals 0. Add the 5 over, and you square root, and you just get plus or minus square roots of 5. So this one has 1 rational 0, 2 complex zeros, and 2 irrational zeros. So it's a whole big mess. But that's okay. We can write the long linear factorization of that, because there's our first 0. Our next 0 is going to be x minus I square roots of 3. X minus a negative negative I square roots of 3. X minus square roots of 5. X minus a minus square roots of 5. And all of that equals 0.